a Blackboard talk on set theory and algebraic topology.
Thank you very much, Benedict, and let me say thank you to you and the other organizers. It's been a great week. It's been a great 4 months or so, and I'm very pleased to be giving this talk here. So my title was Set Theory and Algebraic Topology. That was the title I gave a couple of months ago. I want to focus in on set theory and knot theory, so that's what this will be all about. But knots are fairly closely related to algebraic topology, so I hope you'll forgive me. So this is all joint work with Sheila Miller. And it's about how complex are the invariants that we have for knots. So let me start by clarifying what do we mean by a knot. So the first definition would be that a knot is the homeomorphic image of the unit circle in R3. Okay? Often you'll see people instead of R3 using the 3-sphere. It's 1-point compactification. For our purposes, it doesn't make much difference. And then, of course, there's the notion of two knots are equivalent if you can kind of squish them around to be the same or squish around the ambient space. So the definition is two knots are equivalent if two knots K1, K2 are equivalent if there is an ambient isotopy taking K1 to K2. What does ambient isotopy mean? That means there's a deformation of the space that's homotopic to just the identity, where each sort of slice of that homotopy is a homeomorphism. So the details don't matter for our purposes. Just think of it as the natural idea of two knots being the same up to squishing them, deforming the pieces of rope. Okay, so that's a nice, reasonable definition of a knot, you would think, but you can get some pretty pathological things going on with that. For example, you could have something like this, where you've got a trefoil knot, followed by a trefoil knot, followed by a trefoil knot, sort of shrinking down continuously to some point and then connected around. So you have infinitely much knotting there, and that fits with this definition. So that's bad. That's not what we really want to deal with when we talk about knots. So what we actually want to deal with is, so before I say what we actually want to deal with, there's another reason why for my talk dealing with things that general is bad, and that's because somebody else has already dealt with that. So it's a theorem of Kulikov from this year, or at least appeared on the archive this year. So knots are not classifiable by countable structures. So Vadim already showed that if you allow these kind of wild knots around, then yes, this is an incredibly horrible thing to deal with. So we're going to be interested in tame knots, which is more your intuition for knots for sort of finite things. So definition a tame knot is one isomorphic, equivalent to the piecewise linear image of a polygon. So you take your rope and you just have finitely many straight edges, and that's the kind of knots you're interested in. So that's tame knots, and so there's kind of a earlier converse to Kulikov's theorem, is that due to Joyce, I think a paper of 82, that tame knots are classifiable by countable structures specifically Quandles. Okay, so we've got this class of objects, the Quandles, algebraic objects. I'll tell you in just a moment what they are. And there's a way of associating a Quandle to any tame knot in such a way that if two knots are equivalent, then the corresponding Quandles are isomorphic. Okay, so
Also the convex?
yes, it's a complete invariant, also the converse, that's right. So yes, because it's a complete invariant, you might think everyone would be happy about this, but the knot theorists say, well, these Quandle things, telling whether two of them are isomorphic seems to be a difficult problem. We can't seem to do it in a nice way. So then the question is, okay, how complex is this isomorphism relation of Quandles? And so that's what Sheila and I have been working on, and we've shown that actually it's as complicated as it could possibly be. So let me go on to some definitions, and in particular of Quandles. So okay, so we're going to be considering a set with a binary relation. A binary operation. So A star. Okay, so I'm going to give you a series of structures, each refining the previous one. So the first of these is left distributive algebras. A left distributive algebra is one satisfying the left distributive law I'll number that one. Let me write them over here so I don't erase them. And that's just that A star B star C equals A star B star A star C. Okay? And that's for all A, for all B, for all C. Okay, so this distributivity over itself, that might feel like an unusual algebraic axiom to deal with, but actually there are a few examples of these sorts of things around. So the first case is if you take a group with a conjugation operation. So EGs, so we have a group and then star is conjugation. So A star B is A, B, A inverse. Then you can check, very simple algebra, that this holds for your group with that operation. Another nice example is if you have a Boolean algebra. And A star B is your implication operation. Just A implies B. Then if you take this, put an implication operation there, check with truth tables, you'll find that that works. And another example, which is how Sheila and I got into thinking about all of this stuff, is from very strong large cardinals, rank-to-rank embeddings. So if you have a rank-to-rank, so this is I3 in the table in the back of Kanamori's book, right at the top. If you have an elementary embedding, J from V lambda to V lambda for some limit lambda, and you have another one, K, you can define J star K to be J essentially applied to K. Now K is too big to be in the domain of J, but what you can do is take J of K restricted to V alpha and union that over alpha less than lambda. And it turns out if you do that, you get another rank-to-rank embedding from V lambda to V lambda. And it's easy to check that by elementarity, this is again a left distributive operation. Yes? Implies, or not A or B. Yeah. So that's another example of this, and in fact Lever showed that if you take a single rank-to-rank embedding with this operation and just generate algebraically, you actually get the free left distributive algebra on one generator. So that's how you might have heard about these weird results where you use this very strong large cardinal axiom, a rank-to-rank embedding, and you get finitary results out. It's because they're results about left distributive algebras that we don't know how to prove without the set theoretic machinery of that rank-to-rank embedding example. Okay, so those are left distributive algebras. First axiom. So let's move on to racks. So racks were worked on here in Cambridge by Conway and Rafe when they were students here. So to understand racks, it maybe helps to have a slightly different perspective on left distributive algebras. So we've got this law that's a nice enough algebraic law, but one way to view it is if you take the multiply by A on the left operation, then this law is saying nothing more or less than the fact that that is a homomorphism of your algebra. So if we consider MA taking B to A star B, then the left distributive law is just saying that MA is a homomorphism of your structure for every A in capital A. So then that's left distributive algebras. A rack is going to be one where each MA is an automorphism. Okay, so it's not, each MA is not just a homomorphism, it's a bijective one as well. So in axiom form, you can say for every A and for every C, there exists a unique B such that A star B equals C. And these two axioms together define racks for you. And you can check it very easily that this group conjugation example is still an example of a rack. All right, now on to Quandles. So a quandle is a rack where A is a fixed point of MA for every A. Okay? So that's the intuitive way to say it. The axiom way to say it is very easy. It's just that A star A equals A. Idempotent, right. Yes, exactly. So a rack with idempotence is a quandle. And I want to go one step further down the rabbit hole. Ooh. Do rabbit holes have steps? Probably not. Okay. And that's a K, or also called an involutory quandle. And that's a quandle where each MA is an involution.
Does that word mean anything?
Yes, it's Japanese. It can either mean an edge or it can mean a scepter, like a royal thing. Ks were named by Takasaki in a paper from 1943. It's written in Japanese. Not only that, it's written in classical Japanese, so even Japanese people have difficulty reading it. But apparently K means this. Yes, most of the other work comes from much more recently. Quandles, well, Joyce was 1980s. Quandle is his invention word. So.
Does that mean
No, it's just a nonsense word that he felt sounded right. So the K's axiom is, what's it going to be? It's that A star B equals B. Okay, so those are the axioms we're working with. Let me give you a little bit of geometric intuition. First of all, if you look at groups with conjugation, then you can see, again, it's a quandle, not just a rack. And if you want an example of a K, a good example for that is if you take geometric reflections, so again with conjugation. If you take two reflections and do them one after the other, that's a different kind of symmetry. But if you have reflections A and B and you do A, B, A, then that's another reflection. And the structure of those reflections forms a K. And it was in that context that Takasaki was studying them in the 1940s. How do we get a quandle from a knot? Since I've got it up here, let me give you the gist of it. Let's all right, I didn't even practice that. Okay, so the way you get a quandle from a knot is you take a presentation on two-dimensional paper like this and label the edges. Well, sorry, label the arcs, the connected pieces. And then the Quandle operations that you get, you have to be careful about the orders of things, whether things go forwards or backwards. But essentially it's A going under B gives you C.
So are these directed arcs?
Yes, let's say yes. Right, so what I mean is as it's drawn with the gaps in, I just mean the as drawn arcs. So
It's not really the knot, it's this projection or diagram of.
exactly, it's the representation, if you like. And so Joyce showed that, I mean, you can define it this way, you can also define it in a more directly algebraic topological way, and these are equivalent and they are not invariants. But the kind of gist of it is that you have A going under B gives you C, and that corresponds to your Quandle has three generators, A, B, and C, and then you have relations A star B is C, and this one will have also B star C equals A from A under B is C, B under C is A, and C under A is B. So the Quandle for this knot is generated by A, B, C with these relations. And then if you look at what the Quandle axioms tell you, it turns out there's a very nice correspondence. Each of these axioms corresponds exactly to one of the Rademeister moves. So you might know the Rademeister moves are ways you can, simple ways you can deform knots to get two things that are presented differently to appear the same. Yes, Philip?
Again, the star operation, for example, what is B star A?
So the way I get it is by going around the knot, just follow it around, and so I have A coming under B gives me C, so that's that one. And then I keep going around, C coming under A gives me B, and then B coming under C gives me A.
And what's B star A, for example?
Then you have to, well, you take these are the defining relations of the Quandle. So it's free unless these relations generate a relationship there. So, yeah, that's essentially how it works. And then you have the Rademeister moves, for example, this one. You should have the A going under A itself is the same thing as A. And so that's exactly your idempotence. And the two other Rademeister moves correspond to the two other Quandle axioms. So it's really a quite nice geometric thing. Okay, so that's why we care about Quandles. So now what are we going to, how are we going to show that they're as complicated as possible? Well, first of all, in what sense are they as complicated as possible? Probably most people in the audience have heard of Borel reducibility, but let me state it anyway. So, given two equivalence relations E and F on, let's say, the reals, we say E is Borel reducible to F if there is a Borel map F from R to R such that x is E equivalent to y if and only if f of x is f equivalent to f of y. And we write this as E is Borel less than f. Now, I said the reals, what I really mean is essentially things that can be coded up in a nice way by reals. And what we're going to be interested in, the equivalence relation is going to be isomorphism of countable structures. So isomorphism of countable Quandles, isomorphism of countable graphs, and these things can all be encoded by sets of finite tuples of natural numbers if you assume the underlying set is the naturals. So that can all very nicely be encoded into the reals. So we land in this framework. So the claim, where am I? So we say that a class of structures is Borel complete I guess what I mean is first order class, the usual model theoretic sense of having a signature and all structures for that signature satisfying some theory. So that class of structures is Borel complete if the isomorphism relation of any other class of structures. Sorry? Oh yes, first order, thank you. Class of structures Borel reduces to its isomorphism relation. Okay, so there are a range of classes of structures that are Borel complete. In the very first paper about this kind of stuff, where the term Borel complete is introduced by Friedman and Stanley, they say that it's essentially folklore that graphs are Borel complete. And also, it doesn't matter what you mean by graphs. It can be symmetric graphs, it can be directed graphs. What we're going to use is irreflexive directed graphs. They're all Borel complete. Other examples include linear orders or trees. On the other hand, finitely branching trees is not Borel complete. So, yeah. So then our theorem, oh, I've lost track of boards a bit. Let's. Yeah.
So the orientation you have on this knob, if you take the opposite orientation, I'm assuming you get an isomorphic Quandle.
That's why I was slightly vague.
So in that sense, you don't discriminate with the Quandle up to orientation.
With the slightly hand-waving definition about the orientation definition that I gave, yes, it doesn't distinguish. But, okay, there is a little bit more to it. I said A going under B, but is it B going that way or B going that way? And you have to, if you do it properly, you have to take account of which way B is. So I
guess I simply wanted to say that this, with an orientation, this knot is chiral. And therefore, the Quandle doesn't distinguish between chirality. So you are not just deforming the knots in Euclidean sense, you're also permitting inversion.
Right. If you... Well, if... yes. I guess you're right. Yes. True. Okay. So there's a... You have to be careful about what you mean by equivalence of knots here. So, yes. Okay. Anyway, for Quandles in particular, the theorem is... So... that Quandles are, in fact, let me go one step further, K's are Borel complete. And of course, since K's was the kind of most refined structure of these things, we so too have that Quandles and racks and LV algebras are Borel complete. Left distributive.
Correspond to some specific subclass of knots?
Not really. It's more a case of there's just an assumed involutory nature to the Quandle. I guess you could have K's defined for knots coming from if you threw into the presentation having that A star B equals B for all the generators. Would that do it? Anyway, yeah, sorry, yeah.
Tame knots correspond to all finely generated Quandles, right?
Right.
Defining many relations, so you're talking about only counting many such things.
That's right. So from a Borel reducibility point of view, tame knots is trivial. So showing that these things that we're using as complete invariants are Borel complete shows you that, you know, this is probably not optimal.
You're only using finitely presented Quandles as your invariant.
Sorry, say again?
You're only using finitely presented Quandles as your invariant.
Right.
So that is optimal. Since that's also smooth, as countably many classes.
But, well, no, the point is you can have, there are many, right.
I guess the question then is whether you can, for every finely presented Quandle, you can actually just draw a knot because of it, then it is optimal.
Okay. Okay.
How could a collection of countably many, a class of countably many structures, how can that be Borel complete?
So it's not that.
So, right, this is...
Tame knots, but rather the derived.
I've done a bit of a bait and switch. I've said we're interested in Quandles because of tame knots. Now let's look at Quandles. An isomorphism of Quandles is what the theorem's about. But it's all Quandles that the theorem is about. So, yes. Okay, you caught me. Okay, but anyway, this was, the question remained of whether these things are Borel complete. And so the answer is yes, they are. And how are we going to do that? Encode graphs into Quandles. So we have a way of taking any graph and constructing a quandle, in particular constructing a K from it, and then because graphs are Borel complete, so are Ks, and so are quandles and racks and left distributive algebras. So how does this encoding work? Well, this relies on a result of a much more recent result than all the other history I've been telling you, due to Kamada. And it's about what he calls dynamical quandles. Okay, so here's the construction. Suppose you have, oh, so I said it was recent. It was a 2010 paper. So suppose you have a set A with a bijection tor from A to A. Okay, so Kamada thinks of this pair as a dynamical system. That's where the name's coming from. So then, let's see. So call a function phi from A to the power set of A. Tor replete if for each A, first of all, A is in phi of A, phi of A is closed under phi of A is closed under tor and its inverse, and also the other way you could use tor, phi of A equals phi of tor of A. Okay, so basically this function, given any member of your underlying set going to a subset, it's got to be closed in every reasonable way for the bijection tor. So then the observation that Kamada made, although he set it up slightly differently, but the observation was that there's now a very nice, simple way to define a quandle from that.
From tau and phi.
Right. So then, if you have A for as above and phi tor replete, then with star defined by A star B equals just B if A is in the set corresponding to B and it's tor of B if A is not in that set, then that is a quandle. Okay, It's actually, a couple of these things are very simple to check. The idempotence, of course, is immediate. The second axiom there for racks is just a case of noticing the sort of Tor invariance of repleteness, and then you can check the cases and left distributivity works out as well. So then note also if Tor is an involution, then A with star is moreover a K. So this was so this is the main tool that we use. So how do we use it? Well, we've got this wonderful function to the power set there. That's what we're going to use to encode the edge relation. So I don't want to drag on too much longer, so let me just give you the gist of what we do. So then the idea is encode the edge relation into phi and just have Tor, just kind of tautological. So how's it going to work? Given, let me write that down. So given a graph G, vertex set and edge set, then you can define the K or the Quandle for G with underlying set V times 2, and then Tor is just going to be the involution on the second component. And phi, so Ui is in V, phi of Vj. Well, first of all, you ignore the second component because that's what you need to do to make things Tor replete, and then you just can say that holds if and only if U is an edge, well, U has an edge to V, or of course U equals V. So that's how we define a quandle from a graph. That's the setup, and then of course the dynamical quandle that we get from this setup. Okay, so it should be fairly clear that given two isomorphic graphs, we get isomorphic quandles. The question now is, if we have two quandles coming from graphs, do we, with an isomorphism between them, is there then an isomorphism of the graphs? Now, if you have no fixed points of the quandle, if it's never the case that A star B equals B for all A, so how do I want to phrase this? If B does not have this property, then you take something that moves it with the involution, and then you can take your quandle isomorphism that must move its image, and that will define for you how you can take the vertex corresponding to B to another vertex on the other side. So, all right. So final board, how we do that. So, given rho from QG to QG prime, define f from G to G prime on fixed points and non-fixed points on the non-fixed points case, by the fact that rho is a homomorphism, there's a single choice to make that you're forced. On the other hand, if you're a fixed point, then you can make an arbitrary choice. And then you can go through and check all the mixed cases, and it all works out. And you do get that isomorphism here corresponds to isomorphism of the graphs. So I'll leave it there.
Thank you very much. Questions?
Back to this question about Quandles. So these Quandles that appear in the as in knot invariants,
Right.
finite presented as well.
Finitely presented, yes.
So there are.
Yeah, there's, yeah. Not actually that many of them.
And if you relax finite presentation, well, you still can consider Quandles in general. Is there any class of knots intermediate between these tame knots and the wild knots that would correspond to
That's a
finite generated but not finite presented Quandles?
That's a good question. I can imagine there would be, but I don't know off the top of my head. So, yeah.
So a small question about the algebra, maybe I'm just not understanding properly.
Sure.
So I can see these axioms here. If you have a k, the fourth axiom gets you that in the second axiom the b is unique.
Right.
But if it's a quandle, I don't see it following from the other ones. And you mentioned that you had you're taking the quandle associated to the knot is the free. Well, it's going to be the free quandle modulo some relations.
Right.
How do you fix that? So maybe I'm just trying to.
Sorry, what do you
How
not
do you
get from
ensure
what?
how do you ensure uniqueness of the b? Or does it just happens to be this case in this particular example?
I'm not quite sure.
So you always get free quandles, you say?
Well, no. I mean, you always get quandles from this
Okay. So it's just
construction from
presentation, but it wasn't. It's no such thing as a free quandle.
Well, I mean, of course, there's the term quandle, so there is such thing as a free quandle, but. So another way to express this second axiom is also you can do it with a second operation, have like a star inverse corresponding to, well, the inverse of the multiply by a operation.
Yeah.
And so there, if you do use that approach, then it's purely algebraic identities that you're working with.
Yeah, sure.
So
It's just the uniqueness which was confusing me. Well, what I was getting at is kind of you can't freely generate any quandle on any set. You have a fixed set of generators.
Okay, I guess you might want to sort of bring in the second operation in that case.
Okay.
Yes. With the second operation, you can freely generate. Yeah. Yes.
Yeah, I mean, maybe I'm a bit slow, but can you explain how these axioms correspond to the right Isomorphism moved?
Sure. So. So what are the Reidemeister moves? I have a cheat sheet here. So you've got this in its inverse. So that corresponds to A going under A is A. Then you have actually, even here we'll want the sort of second operation, that if you've got A, B, then this will be B going under A, going under A again, but with the I've waved my hands too much and haven't done the directions for you properly, but this becomes B star A, sorry, right, if, okay, B star A, and then B star A, and this is where I discover that my cheat sheet does right distributive algebras rather than left distributive algebras. So equals B. So this Reidemeister move is corresponding to that second rack axiom, and then
Isn't that the last axiom?
no, because it's this funny second operation that you can bring in to deal with the existential quantifier. Instead of saying there's this, you can say you have another operation star such that A star inverse.
I see.
Yeah.
The B star A is actualizing your existential quantifier.
Right. And then the final Reidemeister move, this goes down to this. Okay. A, B, C, A star C, B star C, A star C. Again, this is right distributive instead of left distributive, but of course it doesn't matter. C, A, B, A star B, B star C, A star B star C. So that's how they correspond. And if you get the orientations right, which is not something I've mastered clearly, then you can do it properly.
Another question following the last question. You definitely have it for the generators. You know, if you've got the knot, and does it follow that if you give relation for for generating a quandle, that you actually I'm not sure what's there.
Shall I say something interesting that's kind of related? So the Quandle axioms are actually a complete full axiomatization of the equational content of the theory of graphs with conjugation. So there is, it's a complete description of something nice. So any statement, any equational statement about groups with conjugation is true if and only if it can be proven from the Quandle axioms. So this was proven by Joyce. So yeah, as for, I'm not quite clear what you were asking about.
Any other questions?
So when you when you encode maybe knots as some kind of finite graph,
Right.
then there's a problem of the complexity of this. I mean, I remember one result which is a consequence of the graph minor theorem.
Okay.
It says that basically, if you want to test such a graph for knotlessness,
Right.
there's a cubic algorithm.
Uh-huh.
And nobody knows this algorithm because it depends on the bad minors, and nobody knows the bad minors.
I see.
But anyway, so is there? So there must be some results in complexity theory.
There are.
Do you know anything about?
So I know that the graph isomorphism, what am I saying? Not equivalence is decidable. But if you go up one dimension and have the equivalent of knots, so surfaces in force space, then that is not decidable. So, yeah, again, there's an important distinction to be made, really, between Borel reducibility and computability. But, yeah.
That decidability is tame knots or all knots?
That's about tame knots, I believe.
Sorry, one other thing. You mentioned the surfaces in full space. Do you get Quandles for those as well, or is it some harder algebraic structure?
You get racks for those, at least.
Okay, yeah.
So, yeah.
No more questions? Is this really the end?
Party time.
Party time. So before we thank Andrew again, let me remind you that it would be nice to use the opportunity to thank all of the Isaac Newton Institute people during the party. So if you could all, well, not all of you, because that would be a bit too much, I guess, but if you feel like it, if you have special moments you would like to thank them for, please thank them for whatever they have done over the last 4 months. And now let's close this whole program by thanking Andrew.
Well, can I just propose we really close by thanking one more time the organizers?